Alright, so let's have a look at some of these applications to exponential functions. Typical questions of these usually involves either decay, growth, or population. Now in this particular one we have a decay one. Alright. The decay of a radioactive substance is modeled by Qt equals to Q naught times 2.7 to the power of negative KT. And you can see these constants are used for various things. Alright, part A. Show that the constant Q naught represents the initial amount of substances. So, initial amount means that our time is equal to 0. If we put in time of 0, then we have Q of 0 equals to Q naught times 2.7 to the power 0. But because anything to the power 0 is just 1, we have Q naught. So we've shown it. B. If a half-life of a substance is 100 years, calculate K to one significant figure. So Q of 100 is equal to Q naught times 2.7 to the power negative KT. Negative K times 100. Now, if you don't know what a half-life means you have half of the original amount. What that means is Q of 100 is also equal to a half of Q naught. So what that means is we can cancel out the Q naughts. So we know that a half is equal to 2.7 to the power of negative 100k. So rearranging this, we would have log of 2.7 of 0.5 equals to negative 100k. So then k is equal to negative 1 over 100 times log 2.7 of 0.5, and then we can just simply put it into the calculator from here, which then gives us 0.007. Now it says to one significant figure, so we can leave it like that. There are possibly more decimals, but we can just leave it there. Or if some of you have been pedantic about it and want to write it in scientific notation, that's 7 times 10 to the power negative 3. But I'm going to use 0.007 to do our answers. C. If initially there was 25 kilograms of radioactive substance, that means Q naught is equal to 25. How many kilograms would decay in 10 years? So we want Q of 10. Oops. So simply sub in the values. 25 times 2.7 negative 0.007 times 10. Put that in the calculator, then we get 23.32 kilograms. Okay, for a set of data, plotting log y versus log x gives us a straight line. So what this actually means is our original graph, if we left it at as x and y, we would get is that we have a straight line still, but the values are really, really big. That's why we use the logarithmic scale. Alright, form the equation of a graph and hence determine the rule connecting y and x. Now, to simplify the way we look at this, you can see that this is essentially a y scale and an x scale. So let's just let a big X equals to log x. Log x. Now if it just says log like this, that means it's usually log 10 of x. Just keep that in mind. and then y equals to log 10 of y. If we do that, then this is essentially just an x and a y, and we have a straight line. So let's just find our x's and y's. So y equals mx plus c. Our gradient, as you can see, will be negative, what is that, rise over run, so negative 3 over 2 x, and then our y-intercept is at 3. Then we go back through and sub in all our values. So we have log 10 of y equals to negative 3 over 2 log 10 of x plus 3. Now, we don't want to have separate values, and in order for us to get rid of the logs, we have to make everything on both sides equal to one single log. So the bit on the left's already fine, we can leave that. However, if you look on the bit on the right, it's not. So let's do a couple of adjustments. First of all, the powers outside can be put into the x, so we have x to the power of negative 3 over 2. Then there's a 3 here, but if we rewrite this with a 1, which is log 10 of 10, we have that. Then we can now put the power of 3 inside. Like so. Then we can join it up as one single log. Now remember, 10 to the power of 3 is really 1000, x to the power of negative 3 over 2, which is equal to log y. Now we can just get rid of them. So if y equals to 1000 x to the power of negative 3 over 2.